Okay, thank you all for coming. Yes, we are starting. It is my absolute delight to introduce Jurić, who is a faculty in the astronomy department at UW in Seattle, and also a senior data scientist and some of their statistical minded institutes, and also he's a lead of the data management team with the LSST. So he's doing a lot of jobs. He's worked his science explorations took him to all sorts of scales. So as a grad student in Princeton, he was working on studied the long-term stability of and evolution of planetary orbits. And then when he moved all the way to IAS, he leveraged then the newly released SDSS data to create a definitive map of the Milky Way galaxy. And sort of the common thread that has been like weaving through all of his work so far has been developing novel computer science and statistical techniques to leverage all of these big data sets to answer astrophysical challenges. So when he was a Hubble Fellow here, he left a lasting legacy and gifted us with a database that is very efficient, cross-matching these large data sets that many of us use to this day. And then, he moved to do more of that with the LSST, and then finally moved to UW. So I'm wrapping up here. Most recently, he has sort of returned to his scientific roots of exploring the solar system. So even starting as a high school student, Mario discovered more than 100 asteroids. And today we'll hear how all of this is going to be revolutionized in a very near future. So Mario, take it away.
Thank you, Anna. I'm not sure the word I would use is gifted us with that database. I'd probably use something like gives the burden of using it. So I apologize for that. We'll try to do better next time. But it's great to be here. So I moved out of CFA in 2012, and I think I've been here since a couple of times. It's always great to come back and see the old faces, see the new faces, and to hear what all of us have been up to over the intervening years. So I'm going to talk about the solar system, the LSST. I have to warn you that this talk has been written and will follow large project rules, which means it's overscoped, under-resourced. It's likely to be not well supervised until the very end, but it will finish on time by definition. And then whatever's left over, we can talk about in discussion. So first of all, let me just point out that my role these days is the person who writes the PowerPoint slides. The folks who actually do the work some of them are here on this slide. Lynn Jones, Sarah Greenstreet, our research scientists, Siegfried Engel recently joined us, and the two graduate students, Joachim Wentz and Hava Smotham, who have done the bulk of the work that I'm going to talk about here. So I will be trying to make a case that the solar system is becoming very interesting, and that with LSST we're going to get so much information about the solar system that the first couple of years we'll go up by order of magnitude. So to give you some introduction of what we're talking about, here is a very simple chart, very simple graph of what the solar system populations look like. So when I was young, the solar system consisted of, relatively speaking, the solar system was planets, satellites, you had your asteroids, you had your comets, and that was more or less it. These days things got a bit more complicated. We've discovered the Kuiper Belt population. There are different subpopulations within the Kuiper Belt, there are different subpopulations within the Asteroid Belt. There are all these kinds of strange objects that we're discovering. There are now interstellar objects that have come in. So the whole place has become a lot more dynamic and I would say information rich. To start from kind of big inner solar system going out, when I say asteroids, this is what I'd like you to think about. They're basically big rocks and boulders in space. This one here has a space needle actually in one of these pixels. It's about 1 pixel in scale. Most asteroids are located in the main asteroid belt. This is a nice visualization that Alex Parker put together of asteroids observed by Sloan. And as I'll tell you soon, with LSST, in about 5 years from now, this sample is going to go up by a factor of about 8 to 10. Moving out from the inner main belt, we get to the region of the Kuiper Belt. There, the population changes in composition, whereas the asteroids in the inner solar system or small bodies in the inner solar system are generally rocky. In the outer solar system, we're talking about icy bodies, things like methane, things like water, things like ammonia, dwarf planets like Charon and Pluto. And the reason why they're interesting is what they are and where they are tells us a lot about the history and structure of the solar system. So one of the kind of early examples of that was this proposed NICE model that tried to explain a number of things about the distribution of orbits in the both inner and outer solar system by inferring from that distribution that the solar system must have started as a much more compact place and then the planets moved outwards. And the interesting thing about this model was that it actually included the possibility that some of the planets may have been ejected and that some of the planets may have changed places, so Uranus and Neptune. So I think it started it made us think about whether the solar system is a much more dynamic place than we used to think. These days, there's a lot of discussion about whether there are more major planets in the outer solar system that we don't know about. This, I think, this case was made most prominently recently by Brown and Batygin with the so-called Planet X. But there are a number of different lines of evidence for potentially Neptune-sized or even Earth-sized planets in the solar system. Maybe not just one.
Is Planet X in addition to Planet 9 in the Kuiper Belt? Or
so this is, depending on which theorist you talk to, there may be one or more, and they may be different masses. So, I mean, my conclusion from a more recent conference is that it may be a discussion about how many there are, rather than one. Oh, yeah, well, X as in variable in this case. For the Brown and Batygin one, the evidence is the alignment of orbits of a number of highly eccentric, highly inclined objects in the outer solar system. So the question is, what put them on those orbits? And they argue if you had a massive body out there, it could create that alignment. There's another line of evidence for perhaps a slightly different object from Reni Malhotra and Kat Volk, where the midplane of the Kuiper Belt seems to have some wiggles. And that you can explain if you put an Earth-sized planet somewhere as well outside the solar system. So it's circumstantial, definitely.
Much of the evidence that we have is in the plane, right?
Mm-hmm.
I mean, how much more is allowed about the plane?
For where these planets
objects.
might be?
Not this object necessarily, but we haven't really searched as much, right?
That is true, yes.
And with LSST, that would
Yeah.
be...
So that's part of my argument why this is going to become very interesting in about 3 years. Yeah, exactly. Good point. The last thing I want to show you in this brief introduction is interstellar objects. So 2 years ago we got our first one, Oumuamua. I guess I should be saying 3 years ago. Yeah. And last year we got the second one, the comet Borisov, or interstellar object Borisov. These are objects that are on highly eccentric orbits. It's unlikely that they come from the Oort cloud. They're passing through the solar system. They originated in other solar systems. Based on this sample of 2 and what we know about the current observing capabilities, we think LSST is going to likely find orders of tens or more. So we're going to get 1 or 2 of these per year coming soon. Moving back to the Earth solar system, no asteroid talk is complete without a video like this. There are asteroids that come too close for comfort. This is the most recent one from February 15th, 2013 in Chelyabinsk. There was about a 20-meter object that entered with 30 kilometers per second, entered the atmosphere, exploded about 30 kilometers above a place called Chelyabinsk in Russia, and caused a whole lot of property damage down below, sent 1,500 people into hospitals, and so on. This was a close call, because if this object came in under in an orbit that was slightly less grazing, it would have actually reached the ground and potentially caused a lot more damage. So these things are also interesting for planetary defense reasons. We get one of these every 50 to 100 years, and as the Earth is becoming more populated, the chance of them hitting a very populated area increases. Not all of them are dangerous. You get some that come close to Earth and get temporarily captured. We call these Minimoons. So at any given time, Earth actually has likely 2 moons, not just one. The difference is that the other one is probably meter-sized, so you don't see it, you don't know about it. We know of about 2 of these. There's 2006 RH120. These come in, stick around for a couple of months, and then leave. These are interesting because you can actually send out a probe to grab material from these at a fairly low cost, and also practice planetary defense maneuvers.
How much time do you have?
You have to, depends on when you discover it. So if you